Hello everyone, I am Yasas from Bioengineering Department at Mississippi State University. My research focus is to predict soil hydraulic properties using spectroscopy. Soil hydraulic properties describe how water moves and stores in soil. We can understand that by using soil water characteristic curve. This curve describes how water hold and release from fully saturated to complete dry conditions. We can use this curve and MVG equation to derive soil hydraulic properties such as field capacity, permanent wilting point, and available water content. The problem is traditional methods to develop this curve are expensive and time demanding. As a solution, we need cost-effective and efficient alternatives to these traditional methods. So our objective is to use those alternatives such as Pedotransfer functions and spectroscopy to predict soil hydraulic properties. Let's see how we did our analysis. We collected 335 soil samples from 0 to 5 centimeter depth, representing from Mississippi and Texas. These highlighted counties shows where we collected our soil samples. In the methodology, we followed three main steps. We used centrifuge method as our standard laboratory method. This figure shows top view of the centrifuge. We can insert 4 samples at once. However, the main drawback in this method is it will take 3 to 4 days to complete the measurements to derive soil water characteristic curve. The second step, we use Pedotransfer functions. Pedotransfer function is a model where it uses easily measurable soil properties to predict soil hydraulic properties. As the Pedotransfer function, we use Rosetta 3, and 2 different models were used under Rosetta 3. In model 2, input variables were sand, silt, and clay. In model 3, input variables were sand, silt, clay, and bulk density. The main drawback in this technique is we need to put an effort and money to derive these input variables. In the third step, which is our main research focus, we use spectroscopic modeling. We use 2 different spectral regions and 2 different soil scanning conditions to predict soil hydraulic properties. Let's move to results and discussion. This figure shows soil property distributions from the soil properties we used as input variables and we derived in this study. This figure shows comparison between Pedotransfer functions and spectroscopy. First 2 columns show Pedotransfer functions outputs from model 2 and 3. Last 2 columns are showing spectroscopic model outputs from visible near-infrared region and mid-infrared region. 3 different rows showing 3 different soil hydraulic properties such as field capacity, permanent wilting point, and available water content. The x-axis of all the subplots show measurements using centrifuge method, which is our standard laboratory method we selected in this study. When we consider R-squared values, we can see lower accuracy when predicting all 3 soil hydraulic properties using Pedotransfer functions. However, when we use spectroscopic techniques, we can see higher R-squared values for field capacity and permanent wilting point. Moving forward, I'll describe how this spectroscopic modeling happened. We have 335 soil samples and we consider it as a data set and we split randomly into training and testing data set. We use training data set to develop our models and we use that developed models and testing data set to make our predictions. We iterated this training and testing split for 50 times to derive this figure. Since field capacity and permanent wilting point worked well, we use only those 2 properties in this figure. And the x-axis shows different spectrometer types and soil scanning conditions as I described here. In this figure, we can see a similar pattern in predicting field capacity and permanent wilting point, where partial least squares regression shows the highest accuracy followed by ridge regression. However, when we use AT spectrometer, we can see a different pattern where random forest shows the best performance followed by categorical boosting. We suspect this variation is mainly due to the differences in spectral acquisition. From these findings, we can say spectroscopic-based models outperform Pedotransfer functions. And when we consider spectroscopic techniques, we can say mid-infrared regions outperform visible near-infrared region because mid-infrared region can capture fundamental molecular vibrations while visible near-infrared region can capture only overtones and overlapping peaks. The impact of this research is we can use mid-infrared spectroscopy as a reliable and cost-effective tool for estimating soil hydraulic properties. This enables rapid soil health assessment and support data-driven water resource management at larger scales. In future research, we should explore the use of fresh soil samples for spectroscopic scanning to bypass soil sample preparation steps such as fine grinding and non-fine grinding. These are my references, and I would like to mention the findings of this research are compiled as a manuscript and submitted to a peer-reviewed journal, and it's under review. Thank you.